Okay, we'll go from current slide. Okay. The announcements, I think you've heard them all before. I'll just go over them real quickly. Mr. Rossi on the Birmingham campus, West Campus, is always looking for math team members. So if you're interested at all in doing that, they meet Fridays at noon and C100 on the Birmingham West Campus, and then Mondays at 3, same place. Okay. Tutoring, if you need that, down the hall here is SSS tutoring on this campus. This is in room 202. If you don't see anyone there to talk with, go on around the corner all the way to the end of the hall, around the corner. Last office on the right is room 212, and they will take care of you there. And this is Josh, right? No. Huh? Tyrell, okay, yes. I got you marked. Okay. And then downstairs from there is the Space Center, and there's tutoring there. Now, over on the Birmingham campus, they've got both of those, SSS and Space Center, but they also have the STEM lab that does some tutoring. All right, so if you need tutoring or if you made good grades in lower level courses, you can probably sign up to tutor. They're usually very happy to have you come in. All right, now the other announcement seems like almost the rule rather than the exception now. Most Fridays I'm supposed to be on the Birmingham campus 7:45 to 11:45. However, last Friday I had an infusion. Friday before that I had professional meetings up in Jasper. I think I was there the Friday before that. The 3 Fridays before that, though, I was having infusions. And this Friday I've got my annual physical. So I won't be there for 7:45 to 11:45 unless the physical gets over early. And I think they've called a meeting for some time on Friday. I haven't seen the time that I remember. So if I get through the physical in time, I may head to the Birmingham campus so I can be there a few minutes, have a little bit of office time, but mostly to go to the meeting. So that's, like I said, it's really getting to be crunch time. And I don't want y'all to feel at all bad about this, but I'm missing a faculty meeting because of you, But I told them I just couldn't handle it. A mini-term course right in the middle, and they said, okay, I could go. So y'all are worth it, though. So, but it does make me feel awfully bad to have to miss a faculty meeting. Right. Let's move on. But anyway, most of the time on Friday, I probably won't be on the Birmingham campus. Maybe there a little bit toward the end. Just depends on how the physical goes. All right. Any questions from whatever we've covered so far? Let's go over a little bit of how today's going to play out. We're going to start in chapter 2 where we started last time, and we'll go from now until 3:15. 3:15 we move to the lab and have a lab, and that goes until 5:15. Okay? Thought I had you in sight, but I don't. Courtney, right? Yeah. All right. Anyone else come in since I called roll? So at 3:15, which is earlier than normal, okay, we go to the lab, and the lab today, I can almost guarantee you will, oh wait, I just remembered. We're supposed to start with the lab. Finish up what you were doing last time, right? Okay, sorry. Hold off on this then. Right now we'll start with finishing off the lab. I hope everybody brought it, right? Okay. Get them out and let's see if there are any questions or anything we need to do. Is anyone here that was not here on Thursday? Yeah, I'm trying to think what day it was. Everybody got a copy of the lab, okay? So, hopefully, then if everybody was here, I am recording, so this is fine. I just wanted to point out, page 1 you should have read, and we did the procedure of Part A, pretty close to that, and then we did the procedure for Part B. Now, after the last thing that we did with Part B, there's on page 16, there is a question 6 that says, describe a pattern or generalization concerning the volume of a cube and its surface area to volume ratio. For example, if the volume of the cube increases, what happens to the surface area to volume ratio? How do these two quantities change together for larger and larger cubes? So anytime you see on your labs a question, if there's not much space there, it's usually just giving you instructions. If there is a space there, they expect an answer. And I expect an answer. So be sure you don't leave that number 6 on page 16 blank. Okay? You get a name, please? Name? Laura. Laura, got it. Vanderbilt, right? Okay, good deal. We were talking about the lab that we did on Thursday. Did you bring it today? Okay. So be sure you fill in number 6 on page 16. Then we did the procedures for Part C. And then notice on Part C, name please? Alexis. Okay, got it. All right. Okay. On Part C, on page 18, notice questions 1 through 7 don't have much space between them. But number 8, 9, 10, and 11 have space. They expect an answer. I expect an answer. Okay? So make sure you fill those in. You may have already. I was telling you in the lab too. I just don't know that everybody did. And then on pages 19 and 20, it's results. And these you answered based on what you found in the 3 parts that we did. Then on 20 and 21, there's a problem there based on this one cube of aluminum. Big old heavy cube of aluminum. And they give you the dimensions here and the mass, and then they ask various questions about that, and you proceed to do all those questions, 1 through 7. Okay? If you did the lab, and I think all of you were there, you should have already filled out your data pages 23, 24, and drawn a graph on 25. I think everybody got that done. Right? Well, actually, the graph page is not numbered. So, any questions on those that you were missing? This is still lab time, so you can work together, work among yourselves, and if you have questions, please ask me. Okay? Any questions on how to proceed, where to go, what to do? Okay. Let's wrap this up as soon as possible so we can get back to Chapter 2. Any questions right off the top? Okay. Then what I'm going to do is pause the screencast-o-matics. All right. Okay. Waiting for the projector to start. And for some reason, here we go. All right, last time we started talking about measuring motion. What were some of the characteristics of motion? What has to occur if you have motion going on? Say again?
Something has to be moving?
Yeah, something has to be moving. What are some implications of that?
Position.
Okay, change of position. Very good. That change of position is often measured in a distance. In fact, it's always measured in a distance. So we have a change of position or change of distance. Another way to express it is change of displacement. Okay? You have a change. What else is happening? It takes time, okay, for that motion to occur. And those two quantities are going to contribute to what we call speed. Speed is a change in position with respect to time. Now, when they say with respect to, that means divided by. You know, change of position per change of time. Okay? Now, average speed is the most common measurement. Okay? After I graduated from college, I had a commission in the Navy, but had to drive across country to get to San Francisco to be flown to my first ship, which I was going to meet in Guam. So, but I drove across country, and just to kill time, because that's a very boring drive, I was always calculating what my average speed, gas mileage. I was just doing lots of things just to keep the time going. And average speed was one of them, you know, measuring how far I traveled and how much time. Okay? Now, instantaneous speed is much harder to measure, but we have, and what's the difference in instantaneous speed? Average speed was how far we traveled over a certain time interval. Okay? A definite. Now, for instance, let's take an example. My trip in from home to here, every morning, I'm just going to round it off to make the math easier, about 20 miles. Okay? Depends on the route I take, but it could be a few miles more, a few miles less, but let's just say 20 miles. Okay? Now, I can usually make it in less than half an hour. Okay? So what would be my average speed if it was half an hour? Say again?
30.
Okay. Okay. 20. Say again? Okay. I said that wrong. 20 miles in half an hour. Yeah, would be 40, right? 40 miles per hour. Does that mean I was driving 40 miles per hour the whole time? No, definitely not. If I was driving 40 miles per hour on the interstate out here, there'd be a lot of honking going on, and probably people waving or something like that, and maybe even yelling nice things to me. Okay, so I wasn't. Part of that trip was in town, where I was stopping at a stop sign or stopping at a stoplight or waiting for traffic before I could turn. So yeah, part of the time I was sitting still. But part of the time I was going probably pretty close to 70 miles an hour. So the average speed is the whole length divided by the whole time. Okay? Now, instantaneous speed, let's see. Is it Coco? Whoa, she disappeared. Okay. All right. I thought I saw her. Okay. Okay. So we've got everybody here, or will be here, that's been here. The 4 people we haven't seen, it looks like we're not going to see. Great attendance, by the way, folks. So instantaneous speed would be when that time interval shrinks to 0. But wait a minute. If you have a change of position divided by change of time, if the time is going to 0, can you divide by 0? No. Okay. So it's sort of a limiting type thing. The time is approaching 0. What is your instantaneous speed? Of course, as you are approaching 0 time, you're approaching 0 distance. You know, change of displacement as well, right? In no time, you don't go any distance. But what was the average? What was that approaching as that time interval went to 0? That's called the instantaneous speed. Okay. Now, here is and this is typically the average speed, distance divided by time. Change in position, distance, with respect to the time interval it took to change that distance. Average speed, distance divided by time. You will be using that in the lab today. Okay? Speed is distance over time. All right? Don't know what was there. Let me just make sure they didn't skip something. Nope, doesn't look like they did. Well, they did, but it's not on there. All right, so here's the average speed. This is showing the distance in kilometers, not miles, okay? And if you started at the 50-kilometer marker and went to the 100-kilometer marker, and that took exactly 1 hour to get there, and then 1 hour later at 3 hours into the trip, you're at a 150-kilometer marker. What is your average speed? 50 kilometers per hour, because every hour you traveled exactly 50 kilometers. Whether you average that over the 2 hours, over the 3 hours, over 1 hour, every one. So this was not only an average speed of 50 kilometers per hour, it appears to be a constant speed. Boy, they had the cruise control set and were sticking to it, okay? The average speed between, let's calculate. The average speed, you did it in your head. Let's do it in actually doing a calculation. Average speed. Now, I tend to use a symbol. They just said speed. In just a little bit, they're going to give you an equation here. But in that equation, they're going to call it V bar. Okay? Now, they use the term speed and velocity as if they're interchangeable. They're really not. What's the difference in speed and velocity? Speed is what kind of quantity, and velocity is what? Slightly different kind?
Speed and direction.
Say again?
Speed and direction. The velocity.
Okay, what's that again?
Speed and direction.
Yes, speed. No, velocity has direction. Speed does not. So speed is a scalar quantity. Speed, scalar, SS. A little mnemonic device they all put together. Whereas velocity is a, what's the other one?
Direction.
Yes, it has direction. And what kind of quantity do we name that? Velocity. Another V word. Vector. Vector quantity. Velocity is a vector quantity that does include direction. You're absolutely right. So here they're using the symbol for velocity, but if it was a vector quantity, we'd put a little arrow on top. This is a bar on top. Usually the bar means average. Okay? So I'm trying to explain why they're using this term. And in the book, it's actually an italicized V. I don't write italics very well, so I'm just going to write it like that. But usually if it's in italics, that means it's a scalar quantity. No vector involved. A vector is either going to have an arrow over the top or it's going to be boldface, not italicized, boldface. So this is average speed. What was the formula for it? Distance over time, okay? Okay, and they say do this between 1 and 3 hours. So what was the change of displacement between 1 and 3 hours? Okay, yes. It's distance at 3 minus distance at 1 over time at 3 minus time at 1. Okay? It's a difference. Okay? All right? Now, what was distance at 3? 150 kilometers minus 50 kilometers over 3 minus 3 hours minus 1 hour, and that gives us 100 kilometers over 2 hours, and that would be 50 kilometers per hour. So what you were seeing and understanding was exactly right. But I wanted to go through the nitty-gritty of actually doing the problem so you get the idea. Notice these are differences. Now I'll start using a notation the book typically doesn't use, but I will call this delta D, change of distance over change of time. Delta means final minus initial. Difference, delta, difference. So it's a subtraction. So it's the final minus the initial, final minus initial, or 3 minus 1, 3 minus 1. Whatever you're using as the first is the initial, and the last at the end is going to be the final. Okay? So I'll use that symbol delta, which means difference. Always later minus earlier. Okay? Good deal. Any questions on that? That's average speed. For some, oh, wait. Sorry. I was wondering why nothing disappeared. So here's that formula we just used. Average speed, again, that's an italicized V, so that stands for speed, not a vector quantity, no direction associated with it, is equal to distance over time, which I like to think of as a change of distance over change of time. Delta D over delta T. Okay, and then what you fill in there? Well, they don't show you, but we just did it. Okay. Now, I already talked about speed. How about velocity? What's the difference in speed and velocity? We just said it earlier. Remind me again. Oh, wait. Before we do, just happened to turn the page and see that, and the slideshow is a little deficient here. There is a great figure in figure 2.3. Okay? Figure 2.3, for those who may not have the book with them today, shows distance in the vertical axis and time in the horizontal axis. Now, why did they choose to do them that way? Say that again? Yes, the units are going to be when you do the slope of the line, rise over run, distance over time, which is going to be your speed. Miles per hour, kilometers per hour, feet per second, centimeters per second, whatever you happen to be measuring there. Okay? Also, the distance depends on the time more than time depending on the distance. So we call the distance the dependent variable and the time the independent variable. And you see that's that same problem we just did, 50 kilometers at the 1 hour mark, 100 kilometers at the 2 hour mark, 150 kilometers at the 3 hour mark. This shows graphically what the previous slide showed with the picture. Okay? This sort of sums it up. The slope is then your speed. You're graphing distance over time. The slope, ratio of distance per time, gives you your speed. Okay. Now, the other thing they're saying with this, let's go back here. Can you give me two other equations that come out of that one? Distance equals what? Yeah, you want to do what, the triangle or the circle? Is that what you mean?
Yeah, the triangle.
Okay, triangle. Okay.
Yeah.
All right. Now here, looking at the one that you're given here, the D is on top. That means the speed is down here and the time is there. Average speed is there. So what would distance be? Yes. Average speed times time. And that's exactly what we do. If I drove here and, or if I drove, say, to Montgomery, let's just say that was about, would you say it's about 100 miles? Is that about right? A little further? Or about something? Right, okay. All right. So if I drove, and I'm not going to get on the interstate, dumb choice, but I'll just choose not to, and I go about 50 miles per hour, and let's see. Oh, I'm sorry. Going about 50 miles per hour and drive 2 hours, will that get me there? Yes, because miles per hour times hours. Hours cancel out. That gives me miles, distance. Units are your friends. Don't leave them out. Use them. They'll let you know whether you set up the problem wrong. So that's one new formula. Here was the original. Here's one new one. Give me one more.
Time equals distance divided by average speed.
Average speed, you got it. There's the other one. And you can give it this way. Time is equal to distance divided by time. Velocity, speed is equal to distance divided by time. And distance is equal to velocity, or speed times time. Very good. Okay? So they go into that and give a couple of examples. So let's us, on this blank page, do example 2.1. The driver of a car moving at 72.0 kilometers per hour. 72.0 kilometers per hour. Can you tell me what that's measuring? Speed. And what symbol do we use for it? V bar. Okay, I can't write italics, so V bar. That's supposed to be just a bar. Okay. Drops a road map. The driver of a car moving at 72 kilometers per hour drops a road map on the floor of the car. Okay. It takes him 3.00 seconds to locate and pick up the map. That's pretty precise. So the 3.00 seconds is a measure of what? That's your time or your time interval. You could call it delta t if you wanted to, because it's the time it took him to pick it up. Okay? How far did he travel during that time? So what are we asking? How far? What will answer that? Distance, right? That is the unknown here, the distance. Okay. Now, just looking at this, the data that we have here, what seems to be an issue here? Okay. Your speed, average speed is in kilometers per hour, but your time is in seconds. So you have a disconnect on units. Okay? But it's not too bad because we can convert those units. So let's start, and by the way, what would be the formula for this if we were going to do it? Distance equal average speed time. Yeah. Okay, so everything's going to be multiplied. So let's head out and start multiplying. Well, your average speed was 72.0 kilometers per hour. Okay? But before we multiply by time, I need to get that hours to second. So here's what I'm going to do. This is how I do my conversions. I do a series of blanks like this. Now, here's what goes with the blank. Numbers go here, units go here. Numbers here, units there. And my recommendation to you is always put the units in their place. Okay? So if you're going from hours ultimately to seconds, what unit conversion do you need to make? Okay, we'll deal with multiplying later. What unit conversion do you need to make? You got to go from hours to second. Now, can you do that in one fell swoop, one conversion? Okay, what would you like to do? Hours to minutes. Let's do hours to minutes. Okay, we already got hours in the denominator. See, there it was. So where are we going to need? Always put the units into place. Don't worry with the numbers yet. Deal with the units. What unit goes where? Hours or minutes? Top or bottom?
Hours doesn't go
Okay, I hear bottom and top. Okay, which do I do? Top. If you put hours on the top and minutes on the bottom, then the hours cancel out. Yes, I like that. Now that we've got the units in their place, let's match up the numbers for the units. How many hours in a minute or how many minutes in an hour? 60 minutes an hour. So put the units where they belong. 60 minutes, 1 hour. Okay? Now we still got kilometers per minute. We need it to seconds. So what's the next unit conversion? Minutes and seconds. Which do we put where? Always put the units in their place. minutes on top, and seconds on the bottom. Now you match the numbers with the units. How many minutes in a second, or how many seconds in a minute? 60 seconds is 1 minute. So match them up that way. 60 seconds, 1 minute. Okay? Now, the minutes will go out. Okay? And then we'd multiply by the 3 seconds. 3.00 seconds. And you see the seconds are going to go out. But you know, we have a little bit of a problem here. Do you think we're going as far as a kilometer in that 3 seconds? Probably not. So we might want to get our distance to something shorter than a kilometer. What would be a good choice? Second, meter, okay? That's the next thing down. So let's convert also our kilometers to meters, okay? So always put the units in their place, which goes where?
Your kilometer gonna go on top.
Really? On the bottom, because they're on top over here. So kilometers on the bottom, meters on top, and what's the conversion there? How many meters in a kilometer, or how many kilometers in a meter? 1,000 kilometers in a meter. Is that what you said? Okay. No.
1,000 meters in a kilometer.
1,000 meters in 1 kilometer. That's it. Kilo means 1,000. Okay? So, now the kilometers go out. And now we'll have meters as our only unit that's left there. So what we do at this point is multiply numerators, divide by denominators. Okay? Now I'm going to try to make things a little easier because I don't want to multiply those big numbers. And here's what I'm going to do. I know 60 is divisible by 12, right? 5 times 12 is 60, and 6 times 12 is 72. So I'm going to divide those two by 12. Okay? Now I'll divide this 6 and that 60. That'll be 10. Okay? And then 10 will go into 1,000 100 times, right? I could have just wiped out a 0 at the end. I wrote the whole 1,000. And then 5 will go into 100. How many? 20 times. And there I've done all the math right there. So that gives me 20 meters. Now how far is 20 meters approximately? Say again? Oh, I forgot the 3. 60. Okay. You're right. I thought that was way too short. 60 meters. Okay. Good catch there. 60 meters. How far is 60 meters approximately? Any of you football fans? How long's a football field? About how far? You're not much of football fans, are you? Say again?
Always a 1.5.
How long's the football field? 100 yards. And a meter is just a little. Yeah, okay. Hang on up. He must be in the band. Okay, never mind. Just kidding. Okay. A meter is just a little bit longer than a yard. So 60 meters would be about 65 yards, which is about 2/3 of a football field. Just 3 seconds to get that. Move 2/3 of a football field down the road. Who knows what happened when he was distracted for those 3 seconds? A deer could have come out. A car could have pulled in. Anything could have happened. 60. And by the way, 72 kilometers per hour is not going that fast, folks. I mean, it's moving along, but it's not really all that fast. Okay? Let's see. I think maybe about 50 miles an hour or something like that. I mean, it's fair, but it's not super fast. Okay? Nope. Yeah. 60 meters. Oh, and I left off my 0.0 because we had 3 significants there, 3 significant digits there. I should put that in there. 60.0 meters in that time that he was distracted. Okay? So that gave us some good things on unit conversion as well. Now they did it probably a bit more Oh, goodness, they did it strangely in the book, which they did it fine, but I think the way we did it probably was a little bit better. Okay. Now, let's do 2.2. A bicycle has an average speed. What symbol do we use for average speed? V bar of 8.00 kilometers per hour. How far will it travel in 10 seconds? How far is asking what? Second? Distance. There's your unknown in 10 seconds. What's 10 seconds a measure of? That's going to be your time interval. Delta T, or just 10.0 seconds. Okay? Very similar to what we had before. Same type procedure. How would you get that distance? What's the formula? Average speed times time. But we got to do some unit conversions, right? So let's start with the average speed, 8.00 kilometers per hour times, and what you want to do first? You got to, we're going to change from kilometers to meters, we're going to change from hours to seconds. You tell me which ones you want to do first. I don't care. Huh? Kilometers per meter to meters? Okay, so we'll do a conversion here. Blank, blank. And what unit goes where? Kilometers on the bottom. Meters on top. Once you get the units in the place, then you match up the numbers. How many meters per kilometer or kilometers per meter? 1,000 what? Which way? 1,000 meters means 1 kilometer. 1,000 means kilo, okay? 1,000 meter, 1 kilometer, okay? And that wipes out the kilometers, okay? Now we got to get from hours to something else. So what do we want to go to? Minutes. And where will minutes go? Where will hours go? Hours on top, minutes on the bottom. How many, now match the numbers with the units. How many hours in a minute or minutes in an hour? 1 hour, 60 minutes. You got it. That wipes out the hours. But we still got to get it to seconds. So blank, blank. What unit goes where? Second? Minutes on top. Seconds on bottom. What numbers match up? Second? 20, you said 60? Please say 60. 60 seconds is 1 minute. Okay, right? Pretty hard stuff, huh? All right. And now we can multiply by our time, which is 10.0 seconds. Okay? And now the seconds will go out. Oh, and the minutes went out. They've been dating. Okay, so you're left with meters. So that's going to give you your answer in meters. Now, this is going to work out nearly as nicely as the last one did, but let's do what we can. Let's wipe out a 0 here with a 0 there, a 0 here with that 0 there, so we don't forget that one. Okay? And let's divide 2 into this. That'll be 3. 2 into that will be 50. 2 into that will be 3, and 2 into that will be 25. I'm just doing it. Oh, yeah, doesn't matter. 8 times 25 is?
200.
Say again?
200.
200, perfect. Divided by 9. 3 times 3 is 9. And this will be in meters. So what is that approximately? Looks like 22.2 meters. Okay. 9 will go into 22 times 2 times 9 is 18. Remainder 2. Bring down to 0 again and again and again and again. But we rounded to 3 because both of these had 3 significant digits. So 22.2 meters. Okay, that bicycle will go in 10 seconds About 25 yards, okay? That would be a good guess on how far, a quarter of a football field. Well, you went much slower speed, but much longer time interval, okay? Good deal. Does that make sense? Okay, there is, some of these blurbs are a little lame, I think, okay? Style speeds, observe people, styles of walking. Okay, if you want to do that, knock yourself out. I'm not going to do much. How fast is a stream? Now that's something, actually we're going to be doing something fairly close to that in lab today. It won't be a stream. I'm not going to run water down the hall or anything. But if you want to know how fast a stream going, drop a leaf in at one place, start your stopwatch. Most of your telephones have stopwatches on them, I think. Maybe even your wristwatch does most of that. And then measure some distance down the stream, and then when it passes that distance, stop it. Distance divided by time is average speed. Now, I would drop it in the middle of the stream, because if you drop it near the bank, it's probably going to get hung up or eddy around or something. The middle is going to go faster than the edges, just about always. Same thing's true with air coming out of the vent. Most of the fastest air is coming out in the middle of the vent because everything on the sides is meeting friction, air resistance, okay? And that's always going to be the case. Okay. So, any questions on speed, average speed? Okay, let's move on to velocity. It describes the speed, how fast is it going, but then as you were saying earlier, it also has a direction with it. Velocity is a vector quantity. It's not just a scalar, how fast is it going, it also gives you a direction, in what direction it's going. So I told you it was about 20 miles from home to here. Well, it's 20 miles to the southwest, because I live in Southside Birmingham, southwest. So when I drive home, I'll be going northeast. So if you add that to it, then we can talk about velocities, okay, rather than just speed. The graphical representation of is done by vectors, and I remember this by vector, velocity, vector, speed, scalar, okay? The length is the magnitude, or the scalar quantity. The arrowhead usually gives the direction. Now here's the graphic they're talking about here. This bar is indicating it's going 30 kilometers per hour due east. This one's going 60 kilometers per hour. Twice the magnitude, okay, but same direction. This one's going 60 miles per hour. There's 30, 60, 30, 60, 60 miles per hour to the northwest, okay? So the speed's the same, but the directions are different, okay? So you can have different speeds, same direction, different speeds, or same speed but different directions. All those are good. If you're dealing with average speed, you don't worry about the direction. This would be the same average speed as that. But if you're dealing with velocities with had direction, very different velocities here, because the direction is different. And that's reality. I mean, you can't talk about velocities being the same if the directions are different. Speeds can be. Okay? Whoa! That's all they had on velocity, folks, and in the book it's one little paragraph. Okay, so let's move to acceleration. What is acceleration? When you're accelerating in your car or bicycle or walking or something else, running, what are you doing? Say again?
Moving forward.
Moving forward, okay. Well, you're moving forward if you're going at the same speed, aren't you? You're still moving forward, so something else is involved with it.
Change of speed.
Change of speed over a time interval. What did I say? Every time we get a dimension, a quantity, well, let's take the time rate of change of it and see what we get. So if you have a displacement, okay, or a distance, time rate of change of that is speed or velocity. Well, if you have a velocity, time rate of change of that, that's what your acceleration. That's why you talk about 0 to 60, and who was dreaming about 2.4 seconds or something like that? No, okay. 4.3 seconds, something like that. Change of speed over change of time. That's an acceleration. Okay? The rate at which motion changes, in other words, speed changes or velocity changes over time. Speed can change, okay, or the direction can change. Because velocity, motion is velocity, not speed, not just speed. So if I was going along here, started slow, pick up, I'm definitely accelerating, right? Okay? Or if I started real fast, but then started slowing, that's also an acceleration. It's just a negative acceleration. We call it deceleration, right? But this would be no change. This would be no acceleration. Traveling at a certain speed, but not changing the speed, okay, or direction. However, that even though my speed's the same, my velocity changed. Because velocity has a direction. Here the velocity was here, here the velocity is there. Okay? Same speed but different velocity. Anytime you have a change of velocity, you have an acceleration. Now, how do you know that going around a bend involves an acceleration? Ever driven on a wet or icy road and go to a corner? Okay? If you don't have friction pushing you inward, you hit the tree or the bank, right? Think about Talladega. Any of you ever been? Okay? If you have been, what's the difference in the straightaways and the curves? Say again? A bank, yeah. Those curves are at a really steep bank. Why? Because the normal force of the track on the car is pushing you inward, accelerating you inward. You've got to have that acceleration, otherwise, off the track. At the speed they're going, it would be off the track. So that's why it's really steep on the bend. So you can have speed change, that's an acceleration, or direction change, that's an acceleration because your velocity is changing, or you can have both speed and direction changing. Or you can have it changing in the negative direction like I showed before. You can have a negative acceleration. Okay? If you start fast and end slow. Okay? Because your change here, the changes are always final minus initial. If your final speed was 20 miles per hour, but your initial speed was 50 miles per hour, you have a negative acceleration. Because final 20 minus initial 50 is a negative 30. So you can have negative acceleration. Now we don't use the term deceleration in physics, though you do in everyday English a lot. Okay? So here are some examples, some figures of, here's the car. It starts off at 30 miles per hour, ends at 60 miles per hour. Is that an acceleration? For sure, because you have a change of speed. No change of direction, but a change of speed, so that's an acceleration. If you started at 60 miles per hour, ended at 30 miles per hour, you have an acceleration. Yes, because your speed changed. It would actually be a negative acceleration because your final is less than your initial. Okay? This is at 30 miles per hour always, but it's going around the bend. Is there an acceleration there? Yes, because acceleration is change of velocity over change of time. Here your velocity was in this direction, there your velocity in that direction. All along the curve the velocity was changing, so you were accelerating constantly. Does anyone know what we call that acceleration? It's called a centripetal acceleration. Centripetal, we're going to hit this a little bit later, but I thought I'd bring it up now. Centripetal almost looks like the word, the first part of center. It means center seeking. You're accelerating toward the center of that circle all the way around there. And that's what the bank does at Talladega. Actually, on the interstates, if you notice that, if you go around a curve, you have to have a little bank there. I can remember in the old days, the county roads were always made like this to run water off of them, right? And if you had a curve in there, but it was curved that way, you went around the curve that way and didn't slow down, you're going into the ditch. I mean, there's just no way, because the road's pushing you that way and the centrifugal acceleration, you don't have anything to push you back. So this is an acceleration, and certainly this is too. You're changing speed and direction, so that's definitely an acceleration. Every one of those is an acceleration. The only time you don't have an acceleration is when you're going constant velocity, which means constant speed at the same direction. Okay? The only time you have zero acceleration. Okay. Now, we're going to hit a concept here. Let me not get too far ahead of myself. Okay. Okay. Yep, I was just about to do so. All right. Okay. We'll probably do a problem there, but before we do, let me point out a couple of other things to you. A couple of good graphs here. You notice the lab loves graphing, okay? And most of the labs you get out of the lab manual, you're going to have graphs with them. Not all, but most of them you will. Those I tend not to do as many graphs, okay? But now we're going to do on our scale here, not distance over time, we're going to do speed over time. So the slope of that line is going to be
that's gonna be our speed. Gonna stay at 1 at a time.
okay. So that would be, the slope would be an acceleration. Well, if your speed was 70 kilometers per hour at time 0, at time hour 1 or second 1, you're at 70 kilometers per hour, and at time 2 seconds, you're at 70 kilometers per hour. 3 seconds, 70 kilometers per hour. 4 seconds, 70 kilometers per hour. Guess what? Yeah, it's a horizontal line. What's your slope? 0. What's your acceleration? 0. If you're going at a constant speed and not turning, you're at a 0 acceleration. Okay? But, on the other hand, if your speed was increasing, so you're at 60 kilometers per hour at time t equals 0 seconds, at 1 second you're at 65 kilometers per hour, 2 seconds at 70 kilometers per hour, 3 seconds at 75 kilometers per hour, 4 seconds at 80 kilometers per hour. What's the slope of that line? Second? 5. Yeah, okay, it's 5 for every second. 5 kilometers per hour per second, that's an acceleration. 5 kilometers per hour per second. That's a sort of unusual term for it because you have hours and seconds in the same term, but it's fine. It makes sense. So that one is accelerated. Okay? Now, they didn't give us the formula, at least on the slide set, and I don't think it's coming. Ah, no it isn't. No. Okay. So let's back up and let me give you the formula. Okay? Average acceleration is v final minus v initial. In other words, change of velocity over the change of time. Now, I like to put delta t there. The book just puts a t. That's a time interval. How much time elapsed? So this is change of velocity over change of time. Now, what's velocity measured in? Give me some typical units for velocity. Second? Kilometers per what? Per hour? So that would be kilometers per hour. And the subtraction doesn't change the units any, but if you divide by time, what time unit you want to use? Hour. So if you did an hour there, it would be kilometers per hour, or you could write that as kilometers per hour squared. Now, most of the time we don't. Most of the time, though, we do use meters per second squared. That's very common. Most of the time we do kilometers per hour per second or something like that. Okay? The other examples have been that. So there are your units. There's your formula. Okay? Now, let's do something with that too. if you multiply both sides of this formula by time, okay, here the times would go out, and you would have, I'm going to switch sides, V final minus V initial is equal to AT. Okay? Now let's just add V initial to both sides, and that gives you V final is equal to AT plus V initial. In fact, I think they usually put, no, that's how they do it too. Okay? Okay? So there's a formula we'll use quite often in solving problems. If you're looking for your final speed, you know what acceleration you have, you know how long you've been accelerating, and what your first speed, initial speed was. There's a good way to find your final speed. Okay? If you think about this as meters per second times second would be meters per second plus meters per second would be meter per second. Yeah, so the units work out nicely. Units are your friends, so keep up with them. Okay. Now they finally get around to showing the delta means change in, and it's always final minus initial. So let's go back. Since they show it in the book now, I'll show it here. V bar is equal to delta D over, they just say T. I like to call it delta T as well. Whereas acceleration, the average acceleration is delta V over your time interval. And we will use that one in lab today too. Guaranteed. Okay? If we get to do lab. How are we doing? Woo! Better move on. Okay. So let's look at example 2.3. All right, to erase that, or someone need a little longer to write it down? You okay? Okay. Example 2.3. A bicycle moves from rest. What in the world does that mean? If it's moving from rest. What's that? What's zero?
No distance at all. I mean, no distance per time.
Okay. From rest means zero velocity. I'm here at no, I'm not moving, so therefore I'm at rest. If I start moving now, I'm moving. Okay, I have a velocity. So from rest means zero, and if it's from rest, that means initial velocity is zero. So from rest, that translates to VI equals 0. Okay? That's how that translates. So a bicycle moves from rest to 5 meters per second. What you reckon that's going to be? That's your final velocity. That's the meters per second is a velocity. Okay? So that's going to be your final velocity. Okay? In 5 seconds. They're into fives, aren't they? Okay? 5 seconds. What's that going to be? That's going to be your time interval. Okay? The question is, what is the acceleration? That's the unknown. That's what we're looking for. Okay? Now, what formula did I just have on the screen? I told you how to do it. A is equal to change of V over change of T or time. And what's your delta? What does that represent? Which V? Yes, that's it. Delta is a difference, so it's a subtraction. V final minus V initial over your time interval. Okay? And what was your V final? 5 meters per second minus 0 over 5 seconds, and that would be 1 meter per second, which we could say is 1 meter per second squared. There's no such thing as a square second, but that's what we mean. Per second is per square second. Okay? And that's exactly what they have there. Example 2.3. Let's do 2.4. Whoops. Let's do the next slide first. Okay? Uniform acceleration. What does that mean? That means constant straight line acceleration. Okay? So going around the curve, that's not uniform acceleration. Okay? But accelerating in a straight line, going slow and then going faster, that's uniform acceleration. Going fast and then going slow, that's uniform acceleration. Anytime it's a constant acceleration in a straight line, that's what we mean uniform acceleration. Okay? The average velocity simply relates to the initial and final velocities in that case. Okay? If you're turning around a curve, you can't really talk about average velocities, because that's directions and could be speeds too. But if it's straight line, uniform acceleration, that means you have, it's just like average score. Say you had 2 tests, okay? Your first test and your second test. What's your average? How do you get it? Add them together and divide by 2. In the lab that we did last time, you had these ratios of circumference to diameters. You had 9 of them. You added them together, divided by 9. That's how you get average, okay? So here is another way to get your average speed. Average speed can be final velocity plus initial velocity plus now divided by 2. We'll use this in the lab too. When you have uniform acceleration, meaning constant straight line acceleration, then you can use this formula. Whatever your initial speed was, your final speed, add them together, divide by 2. And what does that mean? That's your speed right in the middle. If you started there, ended there, and you were constantly accelerating, your average speed is what it was right in the middle. Average between those two. Okay? So we'll use that in today's lab as well. Okay? Now, let's back off and do example 2.4. An automobile uniformly accelerates from rest. What does that mean? You said initial velocity is equal to 0. Got it. At 5 meters per second squared. What in the world is that?
That's the what we just got this.
Say again?
Acceleration.
That's an acceleration. Those units are acceleration. That's your A, your 5 meters per second squared. 4 seconds. What's that a measure of? Time. There we have it. What is the final velocity in meters per second? So what are we looking for? V final. That's the unknown. Okay? And we want it in meters per second. Well, everything here is meters or seconds, so we're happy with that. So I gave you a formula a little bit ago that we would use here. What is that one? Do you remember it? If you don't, we could derive it. V final. Let's see if I still have it on the screen somewhere. Say again? Okay, say that again. Whoops. Okay, what's that? V final equal acceleration times time plus V initial. Now here's a way to think of that. I like to write it the other way. The book writes it this way. V initial, that's your starting speed, and this is how much you've accelerated. So that's how much you've increased the speed, that gives you your final speed. That makes sense, doesn't it? What you started plus what you increased, that gives you your final. Right? This is for uniform acceleration, we can do that. Okay? Now, so this will be V final is equal to what's your A? 5 meters per second squared, don't forget your units, times your time, which was 6 seconds, and then add to that 0. Okay. Yeah. This second cancels one of those seconds out, and this gives you a final velocity or speed of 30 meters per second, an excellent unit for speed. Distance per time, meters per second. There you have it. Final velocity. Okay? 30 meters per second. Now, before we move to the next example, Science and Society, top of the page, should be of some interest to most of you. Transportation and the environment. Isn't this been a big concern for several decades now? I can remember, as Mr. Garland Corley used to say, back when I was a boy child, you know, the cars were typically big, gas-guzzling cars. Everybody wanted a V8. They didn't want a little old 6. Our family always had slant 6s because we were cheap, okay? My father was a farmer. We never bought a new car. We bought used cars. And he bought one new truck. And the time I remember growing up, and my younger brother was so proud of it, he went out and took a nail and scratched his initials in the collar. I thought my dad was going to kill him, you know, but he restrained himself. But anyway, that was the only new vehicle he had ever bought in his life. And my brother went out and scratched it with a nail. Okay. Oh boy, my younger brother is a little wacko. Okay. My older brother's well, never mind. We won't get in the family. Okay. But anyway, transportation and the environment. You know what led the way for our cars changing? Not our concern for the environment. Two things happened. Number one, the Japanese market began, they came over and studied our automobile industry. I mean, thoroughly studied it. And then they went home and put the best of what they saw into practice. But of course, Japan had no fuel resources at all. I mean, we had gas, you know, Texas, Oklahoma, various places had gasoline they drilled. We drained them dry in no time, but, you know, we had them. So, I mean, gas was cheap. So we built these great big old luxury cars and drove them around. Well, after a while, you know, Japan couldn't afford to do that. So they built smaller cars, lighter cars, smaller engines, and get much better gas mileage. So that was the first thing. Now, for a while, our cars were vastly superior to theirs, but they put into practice what they learned from us, and soon we're really developing some pretty quality, high-quality cars. And they still are in many circumstances. But then something else happened. Anyone ever heard of OPEC? Oil producing, no, how does that go? Organization of Petroleum Exporting Countries, or something like that. And they decided to cut back on production at some point. And I can remember, I think I told y'all this once, didn't I? When I was a boy child again, but I was driving now, remember when they had gas wars in town? We could buy gas for 19.9 cents a gallon. $1 put more than 5 gallons in your tank. I was okay with that. Of course, dollars were hard to come by back then, but, you know, that was not too bad. Well, in a very short period of time, it went from very cheap. I can remember when it went to 70 cents a gallon, and we thought, oh man, how we can ever go? And then it went to $1 a gallon, and then it went to $2 a gallon, and I think I can remember sometimes when it got up to $3 a gallon, and maybe out in California, maybe $4 a gallon. Now it's scaled back some because they started overproducing again. But by the time you combine the Japanese and some European smaller cars with gas prices going out of the roofs, all of a sudden, a lot of Americans were not minding those made in Japan cars anymore. And then the American car industry had to start catching up. So yeah, we were worried about our environment, weren't we? But we are now, more so. Nice little blurb here, has some questions. You may even find a research paper topic in there. So I'd say take a look at it. Okay, let's do example 2.5. let me erase this if it's okay. An automobile moving, an automobile moving at 25 meters per second. 0.0 meters per second. Okay? Comes to a stop. So what is this 25 meters per second? It's what? No, it isn't, because that's not per second squared. It's per second. Has to be a speed or a velocity, and which one you reckon that is? There's usually two. Okay? Normally it would be, but this one comes to a stop, so that must mean when it was going at 25 meters per second, that was your initial velocity. And what does coming to a stop mean?
Always going down or decelerating.
What does that mean? If it came to a stop, your zero is your final velocity. Very good. Okay? V final. Okay? And it took it in 10.0 seconds. What's that? That's your time interval. Excellent. When the driver slams on brakes, that's how. How far did the car travel while stopping? Not the question I was expecting to see. How far did it travel while stopping? So what are we looking for? No, how far?
Oh, how far? Velocity.
How far? That's the speed. Velocity. That's how far is? How far do you walk today? Are you going to give me meters per second squared? I don't think so. That's how fast how much you're accelerating. Meters per second would be how fast you're walking. I said, how far did you walk? What would you tell me? Anyone got a Fitbit? Nah, y'all wouldn't have Fitbits, right? Okay. I don't have one either. Okay. I had one, but I lost it in the yard, so found it later and it didn't work anymore. I was so sad. Okay. How far? What's that measuring? Second? Okay, yeah, that's a distance. Your distance is what you're looking for here. Uh-oh. How am I going to get distance out of that? Here's a little hint. Oh, we can get our average speed from the initial speed and final speed, divide by 2, and then average speed times time. That'll give us our distance, won't it? So, what are we going to do first? It was just up there. V bar is VI plus VF over 2, average speed. Now we're assuming here when you slam on brakes, that's going to be a constant deceleration. And that's usually a pretty good guess, okay? Your brakes don't suddenly stop and then ease off or slowly stop you, and then it's usually a constant deceleration, okay? So what's your VI? 25.0 meters per second plus 0, oh, I can do that one, divided by 10.0 seconds. So that's going to be, no, I'm sorry, divided by 2. I'm doing a different problem, okay? Divided by 2. Dimensionless quantity, just the units, 2, okay? And what does this give you? 12.5 meters per second. Now I can take that, and what's our distance formula from a long time ago? At least 2 hours? Hour and a half, maybe? Is what? V bar times time. You got it. And your V bar we just got was 12.5 meters per second. And your time was 10.0 seconds. The seconds cancel out, and that gives you 125, right? Meters. How far is that?
That's right.
That's going to be your football field with both end zones. Okay? You're only going at 25 meters per second, slammed on brakes, you're going to skid for an entire football field, including the end zones, and then maybe a little bit more. Whoa. Okay. So, maybe your brakes aren't too good, I don't know, but yeah. So, how far the car travel while stopping? They got 125 meters. There is a 2.6 there, so before we go, let's just get that one done quickly. This is one I started to do. What was the deceleration of the automobile in example 2.5? So what's the acceleration? Give me that formula again. Oh boy, yeah. All these formulas. V, second. V what? V final minus the initial change of speed over your time interval. And what was your V final? 0 minus V initial? 25.0 meters per second divided by, this is the one I was starting to do before, 10.0 seconds. And that would be negative 2.50 meters per second, which is meters per second squared. So that's your average acceleration. Negative meaning you're slowing down, okay? And that's what they got to. And then they have a little blurb here, concepts applied on acceleration patterns. Actually, there's a really neat experiment I saw and heard described. I didn't actually see it done. You got some good strong guys with some scales, regular scales that you would use to measure your weight, and put it on the back. It helps if it's something like a hatchback or a pickup or something like that. Take the brake off, put it on level ground. You don't want it going up or down hills. And then 2 or 3 guys are pushing on their scales, pushing on the car, that measure of force, okay? And the car's in neutral, the brake's off, that kind of stuff, and it starts moving, hopefully, if they're strong enough to do it. And then someone is sitting in the car, lucky him, and every second drops a little speed cone, a little cone out the door, and then you can measure distance, time, and get average speed, get accelerations, get all those kind of things. Pretty nifty little thing. That's what it's sort of talking about there. We will stop here, okay, and pick up next time with forces. Okay, good deal. Any questions before I remove this from the slide? Okay, I'm going to, all right, I'm going to clear the screen here. Okay. All right. Now okay. Let me go back. Let me count how many we got now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I believe Shanika, when she gets back from her other class, will be 21. Am I right there? Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Right. So you'll have 3 teams of 7 each. You have 6 right here. When Shanika comes back, she'll be here. Okay? You have 3 and 4, that'll be a team, and you have 3 and 4, that'll be a team. So let me move this, since y'all are with them. This goes over here. And unfortunately, we only have 2 sets of scales with 3 teams, but it's not going to take you long to measure. You'll find on your inclined planes, okay, 3 balls. 1 metal, 1 rubber, and 1 plastic ping pong, okay? Each scale has 1 each, okay? Each team has 1 each. If you will, go to the scale here, and before you do it, be sure you zero the scale. Whoever's going to be taking the measurement zeros the scale. Now, if you can get the ball to stay on the scale without rolling off, then you're fine. If it tends to roll on you, then you put the weighing pin on, zero the scale with that, and then put the ball in. That keeps it from rolling off. So if you can do it without, fine, or with, whichever, but be sure that you zero before you do. Now, so that's going to be the first thing you do. Y'all can go and start doing that. There's only 2 scales, 3 teams, so as soon as one team finishes, let this other team go and do their measurements. Okay? Now, what you could be doing while you're waiting, I forgot, I'll be right back.
We got 5 grams, 10 grams, 7 grams.
I want that metal.
Okay.
Yeah, we're down 68.
Part, using the meter stick provided, which is 12. Okay, so you over here. Okay. 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 All there through. Okay, you want to go and do your measurements. All right. No, don't start yet. Okay. If you've done your mass measurements, and by the way, what units were you using? Grams. And you put them down too, didn't you?
Yeah.
All right, of course we did. Okay. Now, with the meter stick, that means not the inch side, but the meter side, then what you should do is measure the length of your track. And the length of the track will be going from inside to inside. And you might need to do that to measure to the nearest 1/10 of a centimeter if you can. Inside to inside. Okay? Once you've got your measure, in fact, you can do that. Okay?
Should round it.
Yeah, closest you can measure. The nearest 1/10 of a centimeter. Okay. Yeah. Inside to inside. Mike. Okay, everybody got the mass measurement so far? Yay? All the mass measurements done? Did you get all 3? Okay. I'll get the scales out of your way. Oh, you already got them out of the way. Good. Okay. Now, listen up for how I come back over here so I can talk near the computer. Okay. So what we do now, you've done A on the front page, 1A and 1B. Real simple. Now on number C, it says on the attached data sheet, okay, record the time it takes for each of the balls to roll down the inclined plane at each of the angles of inclination indicated. And I think I set each of the inclined planes to 5 degrees. Check them and see that I did. Now, what we measure from is the lower edge, the edge that's sort of pointing outward. Is it 5 degrees?
Yes, sir.
Okay, 5 degrees. Now, here's what you do. It's maybe not really clear on this, but let me explain to you how you do this. I think they start with the plastic ball, so if you'll take the others off, and the plastic ball, now, there is a stopwatch right here. Now, I recommend whoever releases the ball control the stopwatch. So let me hold the stopwatch for just a minute. And let me point something out to you. Now, one of the stopwatches looks like it's at 7 at the beginning. It's not. It's just one of the LEDs is out. Okay? Those are all zeros. Okay, your start is the button over here on about 1 or 2 o'clock. Start. And that's also stop. That was, what I was just doing was 1.63 seconds. The 1 is the second, and the sort of smaller units, which are not much smaller, 6.3, that's 1.63 seconds. To clear it, come over here to 10 or 11 o'clock and press that, and it should go back to 0. Okay? Do not hit the middle button, ever. It changes the mode, and then I have to figure out how to get the mode back to stopwatch mode. So don't hit the middle button. Start, stop, read it. That was 1.32 seconds. Reset. Okay? Now, the one releasing the ball and doing what you're going to do is hold it right here, the ball here, and when you release it, you start it, and when it hits the bottom here, you stop it. Okay? You'll do that 3 times. Everybody hear that?
Yes.
You'll do it 3 times, and what I suggest is, say, on the back of the previous page, write down the time. The ping pong ball 3 times, and make sure you get it good. Now, some of the stopwatches won't start when they're supposed to, or don't stop when they're supposed to. So if you get a wacko reading, ignore that and do 3 that are relatively close to each other. And they will be in seconds. So write down the 3 times that you get, or more, okay? And then, rather than averaging, let's just do it simply. Throw out the high, throw out the low, take the middle. That's what you write in the column here, under time. That will be in seconds. And you should have 3 significant digits. Maybe 2 later on, but 3 right now. 1.32 seconds, 1.03 seconds. Maybe a 0.97 seconds. Something like that is going to be your first one. Okay? So you take 3 measurements, throw out the high and the low, you record the middle one. Okay? When you've got that done, then see it. Okay? Do it for all 3 balls at that 5 degree setting. Okay? Collect your data. Okay, I must have left my book in the room. Okay, I must have left my disc cover. I'll be right back, folks.
Yeah, and the average we did a middle school. We did a middle one twice and got 1.56. We did a third time it was 1.69 seconds.
Again, take 3 measurements of each ball at each elevation and make sure they're in the same general proximity. If one of them's way off, do another one until you get 3 close together.
Okay, so 1.14. Yeah. I realized I said average speed, not average time.
All right, have y'all gotten your measurements made yet?
Yes.
Okay, your time.
Oh.
Okay, what you can do, since it probably would be easier, go on and increase it up to 10 degrees, and then do the same thing at 10 degrees for all 3 balls, 3 measurements per ball, 3 balls, and put high, low, throw high and low, and do the middle. Be sure you put the base of that at 10, the long edge at 10. Yeah, and you'll keep going down, yeah. And then we'll do our calculations. That way you can do calculations later if you need to. Yes. Yeah, the bottom one goes there. But do the 10 before you do 15. Okay.
That was the middle one.
You gotta do it 3 times.
I don't know the thing. I don't know the thing. 0.96.
Josh here. You didn't see me first. Just want to make sure I didn't misplace it. Oh, we passed 3:45, so I need to call roll again. Okay, and this also helps me learn names and faces again. Okay. Bailey is there. Josh is here. Alexis is here, right? Alexis, oh, here. Tyrell is there. Justin is there. Tef is there. Travis is got there. Okay. Tanika is at the other class.
53.
Cole is there, yeah. Whoops. Okay, Brandon is there, right, yeah.
47.
Joseph Tray is there. Will is there. I see you. Miranda's here. There. Okay. Providence is there. Lauren is there. And Courtney is there. Just missing Shanika. Hopefully she'll be back soon. Okay. Okay.
It'd be 30 to, it'd be the degrees time. Degrees time. What's the equation for?
Volume times time.
You sure?
I mean, not four. Second. First set. I guess
Are you through? Okay. Okay, is everybody through with all their measurements or awfully close to it, right?
Yes.
Did y'all finish all yours? Okay. Now, let me turn back on. Oh, man. I thought I turned that off and I was recording dead time. Sorry about that. But we are now recording. Okay. All of you finished with your measurements of the times. Okay, now we're ready to do... Are you still measuring? Okay. Good? Okay. Now what you do you got all your time column filled up, right? Now what you do is average speed. Someone remind me what average speed is. The formula. Distance over time, exactly. What distance were you traveling there? Go back to page 1. Number B, length. What was that measured in? Centimeters. Okay. Divided by time will give you average speed in centimeters per second. So what you do is take your that one number you got on number B. I'm going to make up a number, it's not right. 47.3. Okay, that's not what it is, so don't use that one. Divided by the time that you got in each blank, and that's where you'll put your average speed next to that. So I hope somebody has a calculator in each group. Hopefully several so you can check each other. So start filling out your average speeds. Okay, what I'm going to do in the meantime is I'm going to take some of the stuff back to the lab so y'all won't be so crowded here. So you be figuring those averages while all of you have done or are working on final speed, right? Okay. Let's wait just a second and let's do, how do we do average acceleration then? How do we define average acceleration? Say again?
Final time divided by 2.
Say that again?
Initial time minus final time divided by 2.
Are you meaning time?
Speed.
Speeds, okay, that's better. And do you divide by 2?
Divided by. Yeah, that's right.
Okay. What are the units for acceleration? Divided by time, not 2. 2 is what you divide by when you're doing average, and you add the initial and final divided by 2. When you're doing a acceleration, final velocity minus initial velocity divided by time, which is your first column there. So you got your final speed. What was your initial speed? 0. So there's nothing to subtract. So divide your final speed by your time, and you get your average acceleration. Right?
Divided by time.